Hello everyone. This is your recorded lecture for chapter 4 in your textbook, and the material mainly goes over topics of data warehousing. Until now, we have covered um, it's a basic introduction to data mining. Then we did some um, distribution measures in chapter 2. Followed by that, in chapter 3, we learned about data pre-processing techniques, right? And now we're going to learn about data warehousing, right? We are not going to go over data cube technology because we don't have enough time and we need to cover frequent pattern mining, classification, outlier analysis, and clustering, which are much more important parts of data mining process. So we are going to skip data cubing, right? But we are going to cover the chapter 4, which is data warehousing, right? Okay, so let's get started. So what all are we going to learn about in this chapter? We're going to learn about some basic concepts of data warehouse. There are going to be some overlaps between the data pre-processing and data warehousing in the beginning. We're going to learn about the data warehouse modeling, which includes data cubing, and OLAP, which is online analytical processing, right? Um, After that, we'll learn a little bit about our data warehouse design and usage, just like you might have learned about how actual database is designed in one of your basic database courses before. Now we're going to learn about how a data warehouse is designed and how it is actually used, some of the functions of data warehouse. And we're going to learn about its implementation and finally how the data is generalized by attribute oriented induction. All right, so we have a quick example to show how that is done. All right, so let's get started with the first section. Okay, so a data warehouse has several definitions, okay? But there is no hard and fast definition that you need to follow for a data warehouse, all right? So here is a basic definition in order to understand what a data warehouse stands for, right? It's a decision support database which is maintained separately from the organization's operational database. All right. So let's take the example of Walmart, right? So their day-to-day operations, transactions that happen when somebody buys a couple of items, those items go into the database as a transaction, okay? So the data warehouse database is different from this transactional database, okay? It's a separate database which contains data that are used for decision support, okay, by our end users who are the basically the data analysts in our let's say the organization of Walmart, who are going to present decisions based on the queries they do on the data warehouse data. Okay, so the database, which the data store in the data warehouse, is different from the day-to-day operational data, right? Now, another quick thing to add here is data warehouse data supports information processing by providing a solid platform of consolidated historical data for analysis. All right. So what it means is, let's look at each of these terms. It contains consolidated data. So we talked a little bit about data integration. So it contains data which has been consolidated over, let's say, for example, Walmart. It contains data warehouse for Walmart would contain all the data from different locations of Walmart together, right? And it contains historical data. That means it contains data from the beginning of whenever Walmart started functioning to today, right? So it contains all the historical data, right? So the operational data are the day-to-day transaction data does not have so much historical data stored in that database, okay? Whereas on the other hand, data warehouse does store the historical data, okay, and all this data is used for analysis, okay, by the data analysts at the organizations in order to make different decisions such as marketing decisions, placement decisions, and about whether they want to keep a product in their shelves or not, things like that. Okay, so what we are trying to say here is the data warehouse data is completely different from the day-to-day transactional data in an organization. Okay, all right, so moving forward, let's give a much well organized definition of data warehouse. Okay, so a data warehouse is a subject oriented, integrated, time variant, and non volatile collection of data in support of management's decision making process. Okay, so this was the decision given by a famous analyst by the name W.H. Inmon, right? So we are going to look at each of the terms which are in this definition underlined: subject oriented, integrated, time variant, and non volatile. What does each of these mean with respect to the data stored in our data warehouse? Okay, so as we move on in the next couple of slides. Okay, now moving on, data warehousing is nothing but the process, okay, the process of building this data warehouse, okay, and using the data warehouse in order to make decisions in your decision making process. Okay, so why did we call that data warehouse is subject oriented? Okay, so the data warehouse data is mainly organized around important subjects such as customer, product, sales, suppliers, okay, these kind of major subjects, all right, rather than on day-to-day or daily transactions of items. All right, so that is why we say that the data in the data warehouse is subject oriented. Okay, so it focuses the data that you have in the data warehouse, it focuses on modeling and analysis of data for decision makers and not on daily operations or transaction processing. So the data analysts are more interested in basically trying to find new information from the data. Okay, they're not interested in simply trying to understand what the sales are, right, for different items and just things like that. Okay, they're not interested in those basic things. They're trying to understand some kind of patterns that they could come up with by analyzing and modeling the data, right? So that is the reason why the focus is major subjects like customer, product, and sales. Okay, so the data, it provides a simple and concise view around major subject issues, and it excludes the data which is not useful in the decision support process. A simple example of this, we looked at attribute subset selection in the previous chapter, right? So that was a part of your data pre-processing process. So in there, what did we do? We selected the data which is useful for data mining, right, in the future. So an example was if you have, let's say, student data, okay, you can completely omit student ID data, because that's going to be completely useless, right? You're not going to learn anything. You're going to learn about any trends or any patterns using student ID. So you just remove that kind of data. So you exclude the data which are not useful in your decision support process, okay? All right, so the data in a data warehouse is integrated, right? So we understand what data integration is. We have looked at the definition of data integration in the context of data mining before, right? When we basically put together the data from different sources, both homogeneous and heterogeneous sources, right? So it could be, an example could be all the data of all the Walmarts in the Norman area are integrated together, all right, to form a data warehouse, all right. All the data which is available, all right. Let's say the databases came in 1990, all right. So all the data from 1990 to now, all right, in all the Walmarts in the Norman area can be integrated together. But what about the data before 1990? The data during that time was kept in the form of files, okay? So we're going to integrate that data as well into along with our current database in order to form our data warehouse, okay? So what I'm trying to say is we are not only combining homogeneous data, right, which is all relational databases from 1990 to now in all the Walmarts in the Norman area, but we are also combining the heterogeneous sources such as files, which older kept files, into our data warehouse. Okay, so you can integrate different kinds of data sources. Relational databases, which form the major part of the database. Then we have simple files or some online transaction records. All right. So these are all some different sources which are combined together, integrated to form our data warehouse data, right? So after integration, we talked about how cleaning is done, right? On the data cleaning is done, and which is also closely related to our data integration techniques. In order to make sure that the data in our data warehouse is consistent and there are no errors, all right? So we already talked about making sure that the data is consistent. For example, in naming conventions, right, you cannot have two columns with the same student ID and student number, right? When you're integrating, one of them should be thrown away. Encoding structures, attribute measures, etc., among different data sources, all right? So you do not have to keep derivable data. You should not keep useless data, all right? So when data is moved to the data warehouse, it is converted. It is in a slightly different form than the raw data which is available on a transactional day-to-day basis. Okay, now let's look at why we call the data warehouse data as time variant. Okay, so the data warehouse data holds data pertaining to a very long period of time as opposed to the transactional database, right? So uh, the data warehouse data actually holds data from, let's say, the day one when the organization was started until today. Okay. On the other hand, the transaction data is basically purged after small periods of time. All right, if you consider a big organization like Walmart, right, there's so many transactions that happen every day, right? They probably keep data for maybe a week or maybe for a month maximum, all right? But they do not keep data which is older than a month, okay? Maybe another interesting thing to think about is usually returns of items happen what in within 15 days, right? Every store has its own number of days before which you can return an item. So let's say it's 15 days for Walmart. Okay, so you can if you buy an item, you can return it within 15 days. So if it keeps the data in the transactional database for 15 days, that's enough, right? After that, that data is not useful because there is not going to be any returns, all right? So the simple way to put it is the operational database has a current value data. Okay, so probably it just has a week's data or a maximum of months data at hand. Whereas the data warehouse data contains all data that probably the data that was gathered from day one when the organization was started until today, right? Uh, every key structure in the data warehouse contains an element of time explicitly or implicitly, right? So every thing in the data warehouse will be associated implicitly or explicitly to some kind of a time or a timestamp, okay? But the key of the operational data may or may not contain a time element, right? Now let's see why we call the data warehouse data as non-volatile. Okay, so it's a physically separate store of data. We have made that sufficiently clear, right? So the data warehouse data is completely different data, all right, from the operational day-to-day data. Okay, so it's a physically separate store of data which is transformed from your day-to-day database, your operational environment database. Okay, it's the operational environment database is transformed, okay, after some cleaning and integration processes, all right, and some pre-processing that is done on our operational data. You get your data warehouse data, which is a physically separate store, all right. Now, the operational update of the data does not occur in the data warehouse environment. All right, so there are no updates that are done on the data which is already stored in the data warehouse environment. So it does not require any of the transaction processing, recovery, or concurrency control mechanisms. All right. So if it's transaction processing data, you have to worry about if somebody has bought an item, someone else should not be able to buy the same item again, right? So you have to do some kind of concurrency control mechanism, some kind of transaction processing, all right? That is, once an item is bought, then it should go down in the inventory, you know, those kind of transaction processing. And recovery, that is, let's say if somebody is not if you're trying to run a transaction and if it doesn't go through, you want to recover your database and go back to the previous state where before the transaction even started, right? So all these mechanisms are required in a operational environment, in a day-to-day operational transaction environment, right? However, the data warehouse data does not need any of these mechanisms. It just needs two simple operations. Initially, loading of data and basically accessing this data. Okay, so it's non-volatile. There are not many changes that that happen to the data warehouse data. Okay, there's only initial loading of data and accessing the data. There is no change to the data which is stored in the data warehouse, and that's why we call the data in the data warehouse as non-volatile. Okay, now this slide is very interesting. Let's look at what are the basic differences between online transaction processing and online analytical processing. Okay, before we start off, online transaction processing involves the processes, the data processes that we perform on our everyday the transaction data, whereas the online analytical processing is done on our data warehouse data. Okay, so let's look at the basic differences between transaction processing and analytical processing. Okay, so who are the main users in online transaction processing? The clerks or maybe IT professionals. All right, so clerks are basically, you can think of all the people who are sitting on the cashiers, all right, trying to run different transactions and generate the bill and sell items, right? So those are the people who are going to use it. On the other hand, the online analytical processing requires more knowledge worker. Okay, so they need to know what they're looking for, what kind of patterns they're trying to mine. Okay, so what kind of trends they're trying to look at. Okay, so it's a more knowledge worker. All right, they're trying to learn about the data from its trends and patterns that they see in the data warehouse data. Okay, so what is the basic function of OLTP? The basic function of online transaction processing is just day-to-day operations, all right? Just basic day-to-day operations, just selling a few items to different people, all right, and generating the reports. Right now, on the other hand, online analytical processing, the basic function is to get is for decision support. All right, so you basically mine the data. All right, there's a knowledge worker or the analyst who is going to mine the data warehouse data, look for patterns and trends, and provide this information in some kind of a visual way or in a regular way to the client, who is let's say Walmart, the organization, the head of Walmart. Okay, and they are going to use this information for decision making. All right, so that is the function of online analytical processing. So the database design in online transaction processing is more application oriented. Okay, so what are the main things you need for the application, right? Are the things that you store, right? So what are the main things? Probably, the name of the items, an ID associated with item to uniquely distinguish it, the date of purchase, and what is the last date you can return by, what is the price of each item, if there is a sale, reduce that. So it's basically application oriented. Okay. On the other hand, the online analytical processing is more subject oriented. Okay, so it's focused around major subjects like customers, suppliers, sales, products, okay, things like that. All right, we already talked about what subject oriented is. Now, what kind of data is stored in the database for online transaction processing? So the data is more current and up to date. Okay, we talked about how it's only data up to a certain, for a smaller period of time is stored for an online transaction processing. On the other hand, for online analytical processing, the data stored is more historical, right, for a very large period of time, and it's summarized, it's multidimensional, it's integrated over various different data sources, and it's consolidated. Okay, now how do you separate them out on the basis of usage? So the online transaction processing involves same kind of functions being used again and again. Okay, it's more repetitive. On the other hand, online analytical processing involves querying, all right, on an ad hoc basis. So if you find something interesting, if you learn about something interesting, you're going to query based on those interesting facts. Okay, so it's on an ad hoc basis. It's not repetitive. You don't have to basically query the same kind of data again and again. You're not going to learn anything new by doing that. All right, so the access that is required for online transaction processing is a simple read-write, indexing and hashing on primary key. Online analytical processing requires lots of scans of the data in order to learn about the data. So what is the unit of work in a transaction processing is a short, simple transaction. On the other hand, in online analytical processing, the unit of work is a very complicated query. Okay. Now, the number of records which are accessed in transaction processing are very few, right? On the other hand, the analytical processing requires to access millions and millions of records, right? In order to look for trends and to mine for knowledge, you have to go over tons and tons of data. So the number of users, on the other hand, for transaction processing is thousands. Okay, so think about how many cashiers you have in one store, right? You have, let's say, 10 to 15 cashiers in one store, and you have what, 10 stores in and around Norman area. Multiply that with the number of stores in Oklahoma City, in the state of Oklahoma, multiplied with the number of stores in the country, right? So that's a lot of people use the transaction processing. On the other hand, the analytical processing is used by much fewer number of people. All right. The database size required is, of course, much smaller for transaction processing because we are storing more current data, right? On the other hand, analytical processing needs from gigabytes to terabytes of data because we are storing historical data here. Now, the metric which tells us about the transaction processing, how it's working, how well it's working, is our transaction throughput. That is how fast our transaction goes through, right? On the other hand, for analytical processing, it's the query throughput, all right? So it depends on the complexity of the query. And the response generated by the query. How many records does it return? So the analytical processing is based on the query throughput. How do you measure how good it is based on the query throughput. On the other hand, transaction processing, the metric of describing it is basically based on how fast your transactions go through, that is your transaction throughput. Okay, so far we have looked at two different kinds of data. One is your operational data, the database holding our operational day-to-day data, and the second is our data warehouse data. Okay, so now we're going to look at why do we need the data warehouse to be a physically separate store of data from our operational day-to-day data. Okay, why exactly do we need both of them to be separate? All right. So the answer is, in order for both systems to have a high performance, right, we want both of them to work at their peak performance. Okay, and the applications of both these databases are completely different. We already looked at that in the previous slide. So the applications or the kind of functions we execute on both these kinds of data are completely different, right? So that's why based on these applications, in order to maximize the performance of our systems, right, which are using these databases, we try to keep them separate. All right. So the basic DBMS, which is used for our operational data. Okay, it's more tuned for online transaction processing. Okay, so it is tuned to function fast for access methods and indexing, for concurrency control, and for recovery mechanisms. Okay, so these kind of functions operate very fastly when applied on our the operational database data. Okay, on the other hand, our data warehouse data is tuned in for online analytical processing. Okay, for more complex queries, right? For more complex OLAP queries, and it has a multidimensional view, and the data is more consolidated. Okay, or it's integrated over different data sources. So you do not need to have any extra useless data in here, all right, in your data warehouse data, so that your complex queries function at their peak performance. All right, so once again, there are different functions, all right, for both the operational database and for our data warehouse, and that is why we have separated the data out, right? And of course, the type of data stored in both databases is also different. All right. So in order to do decision support in a data warehouse scenario, we need historical data. All right. That is, we need data over a very long period of time. However, our operational databases do not store all this. So all this would be missing data, all right? All that data is going to be missing if we try to perform analysis on our operational data. On the other hand, if you try to do our basic access method operations on transactional on data warehouse data, it's going to take a very long time because there's so much data stored in there, right? So the data warehouse data is consolidated or integrated over various data sources. The decision support, once again, it requires the data to be consolidated. Basically, it should be aggregated and summarized from various heterogeneous sources. So once again, we need all the data that is available in order to make decisions, right? In order to do decision support. Now, the quality of data is also different, right? Different sources use inconsistent data representations, all right? If you have to ensure the data quality on the go, these complex queries are going to take an awful lot of time. All right. So if we actually clean up the data and have a data warehouse ready, which can be used for these complex queries, it's going to be much easier. All right. There are several systems which actually perform online analytical processing directly on the relational databases, which are used for the transaction processing, which hold your operational database data, right? However, it kind of works when the organization we are considering is a much smaller one. Let's say it's a small mom and pop shop which has a smaller database, does not need a data warehouse. Okay, but if we are talking about an organization like Walmart, which has several branches in several locations, it's always better to have a data data warehouse which is separated which is physically separated from the operational day-to-day database. Now let's look at the data warehouse database and what the architecture of a data warehouse database look like. All right. So before we try to understand the data warehouse, you can actually separate it out into different layers. Okay, the bottom layer, all right, or the very first layer of the data warehouse contains the data sources, right? They can be all relational databases, or they may also include other sources such as files that we talked about. Okay, so the bottommost layer of um, the or the bottommost tier contains the data sources, all right? And when you put together all these data sources, you perform your ETL operations, right? Your extract, transform, load, refresh operations on all these operational databases put together, right? And then you come up with your data warehouse, right? So the data warehouse not only contains consistent, cleaned data, which is historical and consolidated from all the operational databases put together, right, after the processes of extract, transform, load, and refresh, right? After doing that, you have your data warehouse. It not only contains the data, it also contains the metadata, right? It also contains the metadata. That means it also contains the data about the data which is stored in your data warehouse, all right? So this metadata is used to monitor the data warehouse data, and it also helps in the process of integration of from all the operational database sources. All right, so we're going to look at what a data mart is in just a couple of slides. All right, but data mart can be considered as a data warehouse which is probably for a specific task at hand. All right, so let's say we are trying to do data mining or data mining is constantly done in the area of, let's say, electronics. All right, so all the data warehouse data pertaining to electronics in that organization can be stored in a smaller data mart. Right, so every time a complex query has to be executed, you don't have to execute it on the data warehouse. Instead, you do it on the smaller data mart. Okay, so the data mart is nothing but it's a data warehouse, but it's on a more specified smaller subject depending on your analysis at hand. Okay, um, now, the next level, all right, your third tier has your online analytical processing server, all right? So just like you have your database management system, right, which gives the front end and your database stored in the back end, right? It is a mechanism to tie these two, right? The same way, online analytical processing server helps the data analyst in order to throw complex queries, right? And it basically processes the data in the data warehouse and it generates results. All right, so this online analytical processor can be connected directly to your data warehouse, and if there are more data marts as well present, it will also be connected to the data marts. All right, now the topmost layer of your data warehouse architecture consists of some front-end tools, right, in order for the data analyst to query, all right, to write his query in and send it to the OLAP server. And once he gets the results, do an analysis of the returned results, generate reports, probably come up with some visual techniques to understand the reports, all right? And basically that is how you get started with data mining. So you have the front end tools which are provided to the data analyst in order to access the data stored in the data warehouse or in the data marts via using your OLAP server. Okay, so we are going to consider three different kind of data warehouse models. The first one is the enterprise warehouse, then we have the data mart, and then we have our virtual warehouse. So the enterprise warehouse, it collects all the information about all subjects in the entire organization, right? So if you had just one database that holds all the data in an organization period, okay, that is called the enterprise warehouse, right? The next kind of model is called a data mart, right? So it actually, each data mart, it holds a smaller subset, okay, of the entire company-wide data, which is important or which is significant to a smaller or a specific group of users. All right. An example is, let's say there is a company and there are several teams. Right. There could be a technical team. There could be a sales team. There could be a marketing team, right? There could be several teams. So for example, let's consider the marketing group, right? So the marketing group is only interested in, let's say, some kind of marketing data in the entire the huge warehouse, right? So they're going to have smaller data marts, all right, which are important for several of these smaller groups within the company, all right? For example, they're going to have a marketing data mart. They can have similarly they can have, let's say, a sales data mart, all right? So for different groups in the company, the smaller data marts are what I want to access rather than the entire database, right? So instead of storing the entire database as an enterprise warehouse, you're going to store them as smaller data marts. So there are two ways in which these data marts can be designed. They can be either independent or they can be dependent. All right. So what that means is the data is actually physically stored in these data marts. All right. The other way is dependent. That means this data mart does not really store the data, but it actually stores a link to the data within the big data warehouse. All right. So it's actually, the data actually comes from the data warehouse. So it's dependent on the data warehouse data. All right. So that is your dependent data mart. Now, the third kind of data warehouse model consists of the virtual warehouse, which is basically generates a set of views over operational databases. Okay, that means there is no physical data warehouse. Okay, but there are several views which are more volatile. Okay, views. If you've done database course before, you know that view is a volatile, or it's a virtual description of a table, right? Very similarly, the virtual warehouse actually consists of a set of views over the operational databases, all right? Only some of these possible summary views can be materialized, all right? You can actually physically store only some of these views. So that is a third kind of data warehouse model. Now let's look at the main operations which are used in order to build your data warehouse. So we already talked about our ETL, the extraction, transformation, and loading, which are the basic operations which are used for building our data warehouse. So the data extraction simply means you're going to get the data from multiple data sources, heterogeneous or homogeneous, and you're going to put them, you're going to just extract the data to get from them first, and then you're going to do data cleaning, right? So you're going to detect errors, you're going to look for missing values, right? And you're going to rectify them wherever possible, right? And the next step is your data transformation, right? You're going to convert the data from legacy or from the host format to our warehouse format. So you're going to do a transformation, okay, by removing all the useless data, which is not significant for any analysis, right? And you're going to do a transformation to data warehouse format. Now the next step is your loading, right? Loading includes several steps: sorting your data, summarizing data, consolidating data, computing views over the operational data, checking for integrity, right? And building indices and partitions. So these are several database operations put together which are involved in the process of load. Then finally you have our refresh process. Okay, so in the refresh, what happens is any changes that happen to the operational database data uh, have to basically be moved over to the data warehouse data. So we talked about this a little bit before. So the data which goes in the data warehouse is not really changed on a day-to-day basis. Okay, so whenever changes happen in the operational data, so you actually record all these changes for a certain period of time, and let's say you record it for a month, and you basically do a refresh on the data warehouse data once a month, where you apply all these changes on the data warehouse data. So whenever a change happens in the operational database data, you not go running and make that change in the data warehouse, because that's not very efficient. Instead, you actually record all the changes and you apply all the changes just once on the data warehouse data. Now, let's quickly look at what is contained in the metadata repository of the data warehouse. Okay, it's a little bit different and it is a little more complicated than the metadata of a regular database. Okay, so the metadata is basically nothing but the data which tells you some more about the data which is stored in the data warehouse. Okay, so what all does it store? It contains the description of the structure of the data warehouse. All right, so what is the schema, what are the different views, the dimensions or the attributes which are stored, the hierarchies, derived data definitions, data mart location, and contents. So these are some of the things which describe the structure of your data warehouse data. Okay, and it also contains the metadata of your operational database. Okay, that is the data lineage, things like data lineage. So how far back does the data go, right? Currency of data, that means whether the data is actually active, archived, or purged. Okay, that means is the data in this data warehouse, which is in this data warehouse, is this part of the active in the operational database as well, or is it in the archived portion of the operational database, or has it already been purged in the operational database? Right, some kind of monitoring information such as warehouse usage statistics, what kind of data is being used more and compared to the others, right? Error reports and audit trails. So This basically comes under your operational metadata. Now, what else does it store? The algorithms used for summarization or for the integration process, all right? The mapping from operational environment to the data warehouse environment. Okay, when you basically throw away some of the attributes, or you basically join together some of the attributes to just form a single attribute, so you have to have a mapping from your operational database to your data warehouse. Now, it also stores the data related to system performance, okay? The warehouse schema, view, and derived data definitions. Then it also stores the business data, okay? That means the business terms and definitions, the ownership of the data, and the policies over changing this data. Okay, so as you can see, the metadata repository for the data warehouse is much more complicated than a regular database data. All right, so now we are finished with the basic concepts of the data warehouse, different models of data warehouse, and the different steps of building a data warehouse, what a metadata repository contains. So now we're going to move on to data warehouse modeling, which contains how to build a data cube and how do you perform online analytical processing on the data warehouse. Okay, so now we're going to move to data cubes. We started with tables and spreadsheets, and now we're going to move to a data cube representation for data. All right. Okay, so a data warehouse is basically based on a multi-dimensional data model, which views the entire data in the form of a data cube. Right, so basically when we integrate the data from various sources, all right, so you can think of each source like a page in a book, and when you put together all the pages, that gives you the entire book, right? So it gives you an extra dimension there. So that's why we call it a data cube. So a data cube, for example, and a sales data cube, right? It allows the data to be modeled and you can view it in multiple dimensions. And there are different ways to view a data cube. Um, so so basically, the two main things which describe a data cube are dimension tables and fact tables. All right. So what are dimension tables? Dimension tables are similar to your relational database tables, which contain, for example, which contain the different attributes of a dimension. So let's look at a dimension called item, and there are different attributes which describe the dimension item, such as item name, brand, and type. Or another dimension called time, different attributes which define the time, the day, week, month, quarter, year, right? So these are examples of dimension tables. So the dimension table could be the table as it is in its entirety in the data warehouse, or it could also be just a subset of attributes that a particular user who is doing data analysis is interested in. So so it basically depends on the task at hand, right? So the next thing is your fact tables, which defines your data cube. Fact tables contain measures, okay, such as dollars sold, all right, or number of items sold, right, and keys to each of the related dimension tables, okay. So the two things that define the important parts of a data cube are dimension tables and fact tables, right? In data warehousing, right, an n dimensional base cube is called a base cuboid. Okay, an n-dimensional base cube is called a base cuboid. The topmost, or the zero-dimensional cuboid, which basically holds the highest level of summarization or consolidation, all right, all the of all the dimensions together, all right, consolidated together, it's called the apex cuboid. And the lattice of cuboids forms what is called a data cube. All right, so in the next slide we are going to look at an example of a data cube, and the different dimensions, the summarization of the various dimensions increases, right, going forward. Okay, so this slide actually gives you a good representation of a data cube, which is nothing but a lattice of cuboids, right? So on the zero dimension, you have your apex, or apex cuboid, all right? And you have 4D, that is your 4 dimension, you have base cuboid. Okay, so the zero-dimensional cuboid is a summarization of all the dimensions together. So you have all at the zero dimension. Okay, and then 4-dimension cuboid contains all 4 dimensions together. All right, in the cube, when you pick all 4 dimensions, describing probably a row, right? You have a 4-dimensional, or the base cuboid. All right, so let's look at each of the levels going down from 0 dimension to 4 dimension. So after all right, the fine summarization, you can pick 1 dimension at a time. All right, picking 1 dimension at a time gives you a 1-dimensional cuboid. All right, now if you pick 2 dimensions at a time, all right, if you pick 2 dimensions at a time, there are how many combinations? You have 4 dimensions, and if you're picking 2 of them at a time, so you can pick time and item, you can pick time and location, you can pick time and supplier, you can pick item and location, item and supplier, you can pick location and supplier. Okay, so it's not all permutations, it's all combinations of the all combinations including 2 dimensions. That gives you your 2-dimensional cuboids. Okay, now if you pick 3 items at a time, okay, to describe an entity, if you take 3 items at a time, all right, so how many ways can you do that? You can pick time, item, location, you can pick time, location, supplier, or you can pick item, location, supplier, right? Or you can pick what else? Did I miss anything? Time, item, supplier. All right. So there are 4 possible ways of picking 3 dimensions at a time. Okay. So they're going to give you your 3-dimensional cuboids. Okay. Now finally, how many ways can you pick all the dimensions, right? So there's only one way of doing it, and you get your 4-dimensional or your base cuboid. Okay, that's going to give you your 4-dimensional or your base cuboid. Now let's look at different ways of conceptually modeling the data warehouses, right? So you're going to use dimensions and your facts, right? We already learned what a dimension is, and dimension table is, and what a fact table is, right? We're going to use these two in order to conceptually model a data warehouse. So there are 3 different models we're going to talk about. The first one is a star schema, right? The second one is a snowflake schema, and the third one is a fact constellation. So the first one is the star schema, which is nothing but the fact table in the middle, right? The fact table contains key right, to all the dimensions, right, to all the dimensions. So the fact table points to all the different dimensions, and it's surrounded by the dimension tables. Okay, it's surrounded by different dimension tables, and there are different attributes which describe the dimensions. We're going to see an example of star schema in the very next slide. The next conceptual model we're going to talk about is a snowflake schema. It is a more of a refinement of a star schema where there is a dimensional hierarchy. All right, so we have fact table in the middle. There are several dimensions surrounding the fact table, right? Dimension tables. Now, let's say an attribute in the dimension table can be further expanded using another table. And another attribute in that expanded attribute table can further expanded. So you show the entire hierarchy of such expansions, okay? And it forms a more complicated shape like a snowflake, and that's why we call this a snowflake schema. So the slide after next one gives you an example of the snowflake schema. Now the third one is a fact constellation. When you have multiple fact tables which share dimension tables, right? When you put them all together, then it forms a collection of these star schemas, and it's called a galaxy schema or a fact constellation. There is also an example of this, so you can understand this better. Okay, so this slide shows you an example of a star schema. So you have your fact table in the middle, which contain keys to all the dimensions in your warehouse. So you have your time key, which points to your time dimension, branch key, which points to branch dimension, item key points to item dimension, location key points to location dimension. Right, and then you also have the measures, okay, that we talked about, such as units sold, dollars, of the sold amount, what are the average sales, and things like that. Okay, so then you have your dimension tables surrounding your fact table. So each dimension lists a set of attributes which describe the dimension, right, right below it for each of the dimensions. So this is the example that shows you the star schema. This slide gives you an example of a snowflake schema. So you have your fact table in the middle, similar to your the previous one, but surrounding it you have your dimension tables, just like in your star schema, with the set of attributes which describe each of the dimensions. However, some of these attributes can further be expanded to another set of attributes describing that attribute, right? An example here is you have supplier key as an attribute under the item dimension table, and supplier key is itself another table, and there are two attributes, supplier key and supplier type. So there is another table that comes from supplier key. And a similar way, there's a city key, and there are four attributes which define the city. You have your city key, city, state or province, and country. All right. So you have a hierarchical way of joining together different dimension tables. All right. So an attribute in the highest level of dimension table can be related to a smaller dimension table which contains some more attributes, and if one of the attributes in that table can be linked to another table, right, and so on. So snowflake schema is nothing but a somewhat of an expansion of your star schema. So it gives you an expanded view, which is a little more expanded than the regular star schema. Now we have our galaxy that we talked about, or a fact constellation, okay, which consists of multiple fact tables, all right, which consists of multiple fact tables, and there are different dimensions which are linked to these fact tables together, all right. So basically you're expanding the view further, all right, with a fact constellation. So we started with a star schema, which shows you a more narrow view or a smaller scope, all right. You basically view through a smaller lens for a star schema. You expand on the view further and you get your snowflake schema. You expand it further and you get your fact constellation. Now, let's look at the role of concept hierarchies in the definition of a dimension. So to understand that, let's look at the definition of a concept hierarchy, right? A concept hierarchy is basically a sequence of mappings from a set of low-level concepts to a set of higher level, more general concepts. So we learn about this at the end of chapter 3, all right? Let's consider a concept hierarchy for a dimension called a location, right? In here, look at the city values for the location, for the dimension location. We have Frankfurt, Vancouver, Toronto, right? However, the city values can be mapped to a country to which these cities belong. For example, Frankfurt is in Germany, Vancouver and Toronto can be mapped to the country Canada, right? And you can further find mappings to tell which region the country lies in, or specifically which continent it is in. It could be Europe or North America, all right? So these mappings are basically forming a concept hierarchy for the dimension called location by mapping from a set of low-level concepts, which is from cities, to a higher level concepts, which is countries. Okay, so if you look at it, your apex cuboid contains all of them together, complete summarization, and at the base level we started from city, but the office locations, all right, let's say L Chan M Wind stands for the office locations, all right, where they are located within a given city, all right. So you can actually have a mapping all the way from office, which is your four-dimensional cuboid, all right, and all the way to the summarization, which is all. Okay, so we talked about the dimension tables and fact tables just a couple of slides back. Then we talked about the attributes within the dimension tables. Then we talked about the relationship between the concept hierarchy and your dimensions, right, which is basically similar to the mapping, which is similar to the lattice that you get is similar to the mapping in your concept hierarchy. Now in your fact table, there was not just the keys which link to each of these dimension tables, but they were also measures in the end, right? So what kind of measures does the fact table contain, right? So there are three different categories in which you can actually distribute the possible kinds of measures which go into the fact table, right? So these are three kinds of data cube measures which are possible. So the first one is a distributive measure. The second one, it can be an algebraic measure, or it can be a holistic measure. Right? So let's try and understand what each of these mean. So the first one is a distributive measure, all right? What that means is if you can find the result by applying a function on a smaller subset of values and basically add it together for each of these functions, and you get the answer on the final total set, then it's called a distributive measure, right? An example is count, sum, right? So let's say you have 100 values, right? So if you find the sum of 10 values at a time, right, and you find 10 such sums, and you can basically find a sum using all these 10 sums to get the sum of all 100 values, right? If you can distribute it in such a way, then it's called a distributive measure. Examples are count, right, or sum, or minimum, or finding a maximum of a given set of n values, right? So the next kind of measure is called an algebraic measure, right? So what does this say? If it can be computed by an algebraic function which takes m arguments, right, where m is basically a bounded integer, each of which can be obtained by applying one of the distributive aggregate functions that we talked about, the distributive functions in the previous distributive measures, okay? Then it's called an algebraic function, right? Let's look at an example of that, okay? So, for example, you have a set of values, all right? So if you can find first the sum of all the values, all right, using the distributive measure, right? You can find the count of all the values using the distributive measure, and the sum divided by the count gives you the average. Okay, the min underscore capital N, it is a function which finds the first n minimum values. Okay, similarly you also have max underscore n, which finds you the maximum, the first n maximum values. All right, so these are functions. Once again, standard deviation is also a function of mean or average, right? So your algebraic function uses your distributive measures, all right, functions of your distributive measures to calculate a value, all right? So that is your algebraic measure. The third one is holistic measure. So what does that say? If there is no constant bound on storage size needed to describe a subaggregate, all right, that means there is no way to distribute the number of values that you have and basically additively find the measure, then it's called a holistic value. Example is your median, mode, and rank. Okay, so if you have 100 values, right, you cannot distribute it into 10 different sets, find the median of each of the set, and say the median of the all the 100 values is the median of each of these sets. That's not going to work, right? You have to find the median of the entire 100 values by sorting the 100 values and finding the median, right? Similarly for mode, okay? So that's the holistic measure. This slide simply shows the view of warehouses and hierarchies. Okay, so there are two different ways of picking the level of hierarchy. So it could be a schema hierarchy. An example of schema hierarchy is day is less than month, is less than quarter, is less than week, is less than a year. Right? So another one is basically a set grouping hierarchy, right? Where basically the elements of the set define which group dimension falls into. For example, if it's $1 to $10, something is inexpensive. If it's anything between $10 to $100, it's affordable, maybe. Anything more than $100 would be expensive. All right. So that's called set grouping hierarchies. Then the elements of the set or the range of the sets are decided, and so the hierarchy is based on the value, whether depending on which set it falls into, and that's how you decide which level of hierarchy it belongs to. So here is an example of looking at a multidimensional data, all right? So we're looking at sales volume as a function of product, the month of sales, and the region of sales, right? So the dimensions we looked at so far was your product, location, and time, right? So depending on which level we pick, we will get either a small chunk of the cube or a large chunk of the cube. So if you pick the highest level of hierarchy and in all the dimensions, you're going to get the largest sized cube. If you're going to pick the lowest level of hierarchy in each of the dimensions, you're going to end up with the smallest size cube. So here is an example of a sample data cube. So you have three dimensions, and you have a product on one dimension, you have date on the other, and you have country. So basically the product gives you the sales per product, okay? Date gives you the sales per quarter, right? And country gives you the sales per based on different regions, right, or in different countries, right? So the last column in each of these dimensions is a sum, right? So the product in the product dimension, the sum gives you the sum total of sales of all product, all right? And over the sum next to in the same which is the last column of your date, right? Date dimension gives you the sum total of all the sales in all quarters, okay? Per each product, different products, and for different countries. Now there is a sum for which is a column along with the country dimension, which gives you the sum of the basically based on all countries, all right, in all the countries per product and in different quarters, right? So the blue box, which is in the rightmost, which is shown as all, gives you the total annual sales of all products over all quarters, over all regions, or over all countries, okay? So basically the blue cube is a sum total over all three dimensions, all right? So basically the in your cuboid, the all part of it was is represented by that blue cube. Now let's look at the same sample cube but in the form of a lattice structure, right? Where you see the different cuboids which are forming with respect to the entire cube, right? So you have your zero-dimensional cuboid, which is the apex cuboid, which contained all, right? All the blue cuboid that we talked about. Then we have one-dimensional cuboids where have just product. You can find the sum of just the product sales, or you can find by date and country. You just pick one at a time. Then the two-dimensional cuboids was when you pick two at a time, a product, a given product in a in a particular quarter, or a given product, all right, in a given country, or a given during a given quarter in a given country, right? And the fourth one is your 3D or your base cuboid, three-dimensional cuboid, which contains all your product, date, and country, which gives that some total volume. So this slide lists the typical online analytical processing operations which are available. So some of them are listed here. The first one is called a roll-up or a drill-up, which basically means summarizing data. That means by climbing up the hierarchy levels, right? You're basically summing together the hierarchies and you're looking at it with a higher level of hierarchy, right? By reducing the dimension, right? We look at example of this in the next slide. Then we have a drill down, right, which is the reverse of roll up. So you take a higher level summary and basically split it further into greater detailed data, and you introduce newer dimensions, right? So that is your drill down. Then you have slice and dice, is basically project and select. So you can roll up a certain bit, you can actually slice and dice. So you can select a portion of data even from the roll up and drill down. Okay, then you have a pivot or rotate. Okay, so we looked at cube, the data cube with let's say your product was your x-axis, and your time was y, and the country was Z. So you can reorient it. So the X, Y, and Z changes, so you get a different view, right? Or another way is you can actually convert it from a 3D series to a 2D plane, okay? So it gives you a different view of the data. There are some other operations which are available, such as drill across and drill through. So drill across, it involves more than one fact table. All right, so you have to put together multiple tables to gather the data that you need. For a drill through, you basically are going to drill through the bottom level of cube to the back end relational tables. So that means the lowest level of hierarchy which is available to you is not enough. You still need more detail, and that level of detail is only available to you from your relational database tables that come from your operational database. Okay. Slide shows you all the operations that we defined in the previous slide. So let's start with the roll-up operation, which is shown in the right hand top corner, right, where you have different city values with respect to cities in the middle cube, all right, and the topmost right cube shows that it has been rolled up into countries, right? So you have Canada information and US instead of information with respect to each city. So that's a roll up with respect to your location dimension. Now your the bottom right corner of the slide shows you how drill down is done. So instead of giving the data with respect to each quarter, we are listing the monthly data. So we have drilled down to get a greater detail, right? So we have drilled down to get a more finer detail, right? Now the left side, okay, of the slide shows, the top part shows how dicing is done, all right, and the bottom the middle figure on the left hand side shows you how slicing is done, right, where you're getting only a two-dimensional picture of what you're interested in. And finally you have a pivot, which is the left bottom most picture in the slide, where your x and y axis has been kind of flipped, all right, and you're getting a different view of the data. So this slide shows what is called a StarNet query model. So each of the lines radiating from the center outwards represents a different dimension in your data cube, and each of the circles on these lines radiating out of the center is basically a different level of hierarchy for each of these dimensions. All right. Each of these circles is also called a footprint, and it represents an abstraction level, all right, for each of these dimensions. So if you join together the circles on different radiating lines, you form somewhat of a star net, okay, across all these lines, and basically that gives you a specific net here gives you the size of the cube that you're going to fish out of your data warehouse with this given star net. Uh, So this slide just shows you how you can actually browse a data cube using different online analytical processing operations that we talked about, right? Roll up, drill down, slicing, dicing, pivoting. So all these operations give us the capability to basically cast a small net or a wide net and get some chunk of the data out of the data cube and basically turn around the cube any way we want, using something like pivot operations, and visualize it any way we want, and basically we can interactively manipulate the data cube. So with this, I think we are almost at the end of the data warehouse modeling and the online analytical processing operations. Your next topic is going to be data warehouse design and usage, its implementation, and data generalization by attribute oriented induction. So I'm going to stop here for the first part of the lecture, and I'm going to go ahead and post this. And the second part of the lecture is going to be the remaining three topics. Since this is already an hour and a half long, I'm going to post the rest of the lecture as part 2.